So in this session, we are going to measure the dielectric constant of a capacitor using a calibrated gold leaf electroscope. Now, we should all remember that a dielectric constant, by definition, we know that a dielectric constant is simply referred to as the ratio of the permittivity of the material that is always between the plates of a capacitor to the permittivity of a vacuum. But also another definition for dielectric constant is that dielectric constant is equal to the ratio of the capacitance of a capacitor with the dielectric between its plates to the capacitance of the same capacitor with the vacuum between its plates. In our previous sessions in this series of electrostatics, we were able to explore that in more detail. So we are going to use this circuit to measure the dielectric constant using a calibrated gold leaf electroscope. So let's get to it. So this gold leaf electroscope you're seeing here is calibrated so that it is able to measure electric potential. Yeah. So this simply means that the divergence of that gold leaf is supposed to be directly proportional to the voltage. In other words, the angle of deflection is supposed to be directly proportional to the voltage that it's measuring. So that is why we have here that the voltage that this thing will be measuring should be directly proportional to the angle of deflection. And of course, if we are to remove that, that proportionality sign, we end up with a constant of proportionality K. So that's how we end up with V is equal to K theta. So what happens here is that we are going to first close switch K while keeping K2 open. We close switch K1 while keeping K2 open. Of course, when we close switch K1, it means that this capacitor is going to be charged because this is the only circuit that will be in play. And so when this capacitor is charged, afterwards, then we shall open K1 and then we shall close switch K2. And then we shall close switch K2 while K1 is open. It means that the charge that is inside this capacitor is going to cause this to be deflected. So when it is deflected, it means that the voltage that we are supposed to get from this is equal to K times the deflection, which we've called theta 1. This is coming directly from that. Now for V1 is equal to K times theta 1, we are doing this, we are closing K2 while the capacitor has no dielectric between it, or when it is a vacuum, or when there is nothing between the plates. So again, without discharging the capacitor and without, changing the distance of separation, we insert a dielectric between the, the parallel plate capacitor, and again, we close switch K2, and we are able to get, so we shall go and read off another value of theta when we have inserted the dielectric between the parallel plate capacitor. That is done without altering, the distance between the two plates and without discharging this capacitor. So we insert a dielectric between the the parallel plates of the capacitor, and we are able to read another value of theta, which we are calling theta 2, and so we are able to come up with this expression of the voltage. V2 is equal to K times theta 2. So of course, after coming up with these two expressions, our interest here is that we are interested in finding the dielectric constant. And remember, we said by definition that the dielectric constant can be defined by the ratio of the permittivity of this dielectric to the permittivity of free space, or the permittivity of the vacuum. It can also be defined as the capacitance of a capacitor when there is a dielectric between its plates to the capacitance of a capacitor when there is no dielectric between the plates, or in other words, when there is a vacuum between the plates. So from this, we are simply going to use the second definition. We are going to find the expression for the capacitance of a capacitor when there is a dielectric between the plates to the capacitance of the capacitor when there is no dielectric between the plates. So we all know this expression. We know that charge of a capacitor is given by C times V, C being the capacitance of the capacitor, V being the voltage across that capacitor. Now, when we're carrying out this expression, the charge between the plates of that capacitor is the same in both cases here. So going to case 1, when there was a vacuum between the plates, that is in the first instance, we know that Q is given by the capacitance of that capacitor, which we are calling C times V, and in this case the V is this, so Q times V1, which is going to be Q is equal to the capacitance of the capacitor when there was no air, that is C1 times V1, which is K, which is times K times theta 1. Okay, so that is equation 1. Then let's do the same case for the case when there is a dielectric between the two plates of the capacitor. When there is a dielectric between the two plates of the capacitor, we shall simply come here and say that the charge is between the capacitor, the parallel plates of the capacitor is given by the capacitance of the capacitor when there was a charge between the two plates, multiply that by the voltage V2, and in this case this is going to become Q is going to be C times V2, which so happens to be K times theta 2, like that. So this is going to become our equation 2 right there. So what happens is that we are going to divide this equation and that. In other words, we are going to say, so equation 2, divide that by equation 1 is going to be given by equation 2 is this. So it's going to become Q, which is going to be equal to this C2 times K times theta 2, divide that by equation 1, which is right there, which is Q is given by C1, this is 1, K times theta 2. I'll continue with the working here. This Q divided by that Q gives us 1 is going to be equal to, then this C2 over C1, that's going to be C2, divide that by C1. This constants will cancel out, then we shall remain with theta 2 over theta 1 times theta 2 divided by that by theta 1. Let's make this a flat equation. Well, we can multiply the denominators on both sides times C1 theta 1, C1 theta 1. This goes with that, you remain with C1 theta 1, giving you C2 theta 2. So let's keep the C's. You remember C1, C subscript 1 is the capacitance of the capacitor when there is no dielectric. C2 is the capacitance of the capacitor when there is a dielectric. So if we can simply say over C1 here, over C1, so that you know this goes with that, then we do this over theta 2 over theta 2, so that this goes with that, you shall remain with theta 1 over theta 2, giving us C2 over C1. Remember, C2 is the capacitance of the capacitor when there is a dielectric between the plates. C1 is the capacitance of the capacitor when there is no dielectric between the plates. And by definition, we know that the dielectric constant is given by the capacitance of the capacitor when there is no dielectric, the capacitance of the capacitor when there is a dielectric between the plates, to the capacitance of the capacitor when there is no dielectric between the plates. And this ratio is the same as the deflection that you get when there is no dielectric between the plates to the deflection that you get when there is a dielectric between the plates. So in other words, when we do this experiment right here using this setup and we want to measure the dielectric constant using a calibrated gold leaf electroscope, if we simply get the ratio of the angle or the deflection when there is no dielectric between the plates to the deflection when there is a dielectric between the plates, this ratio is able to still get us the dielectric constant. And so that enables us to find the dielectric constant using a calibrated gold leaf electroscope.